Okay, let's unpack. We often find ourselves looking at population, through the lens of, is there enough water? Can we generate enough energy? Is the climate change?
Right. All incredibly important questions. Complex ones.
Exact. But today we're doing something a bit different. We're going to strip away, just for a moment, all those practical concerns. Physics, logistics, sustainability, even comfort.
We're diving into a pure thought experiment, real geographical mathematics, pushing the boundaries of scale.
It boils down to this. If every human was just a unit of measure, like a tile, how big is the Earth in human tiles?
Yeah, that's a good way to put it. How many people could physically fit?
Precisely. We're asking, what's the theoretical absolute maximum number of people Earth's total surface area could hold? And the constraint...
The constraint being exactly one person per 1 square meter.
Yes. We're using calculations from our source, Global Human Density Calculator, which is built entirely on that incredibly strict premise. 1 person, 1 square meter, period.
And what's fascinating here, I think, is that this isn't about comfort. It's not about survival, even.
Mm-hmm.
It removes all the engineering challenges, infrastructure, climate, everything. It's just...
Well,
it's a pure measurement of surface area.
Translating area directly into human units.
Exactly.
Yeah.
Like defining the planet's two-dimensional skin using people as pixels.
So that's our mission for this deep dive. We're going to take apart the 3 enormous numbers that come out of this: the land number, the sea number, and the grand.
And through that, hopefully, help you visualize the actual geometry of our planet.
By the end, you'll have a really visceral sense of just how much bigger the oceans are than the continents, simply by comparing the people counts.
That 1 square meter rule is the foundation. You've got to imagine this massive, continuous layer of humanity, shoulder to shoulder, essentially.
Tightly packed.
Extremely. It's a boundary condition, isn't it?
Yeah.
Any more people than this, and you'd literally have to stack them or they'd overlap.
Right. It's the absolute maximum before things get, well, even more theoretical. Okay, let's start with the solid ground, the land, where, all of history is happened.
Where we live.
Exactly. So the first major figure from the source is the number of people needed to fill all of Earth's land at that density. 1 person per square meter.
Okay.
And the specific number, 149.
Wow. Okay, let's just let that sink in for a second. 148.9 trillion.
Trillion, with a T.
To give that some context,
Yeah.
Our current global population is just over 8 billion, right?
Yeah.
So we're talking about a number that's more than 18,000 times larger than everyone alive today, everyone who's ever lived, probably several times over.
It's almost impossible to visualize, isn't it? A trillion of anything, let alone nearly 150 of them. Our brains just sort of short circuit.
They do. We don't have a daily frame of reference for trillion. No, I mean, think about counting. If you counted 1 person per second nonstop.
24.
Yeah, 247, no break. To count 148.9 trillion people, it would take you almost 4.7 million.
4.7 million years just to count them.
Just to count them. So that gives you a sense of the sheer numerical scale before we even get to the geography.
Okay, let's get to the geography then.
Yeah.
Because land in this calculation, it's not just, fields and cities.
No, not at all. It means covering every single square meter of solid surface.
Every single one.
Uniform coverage.
Yeah.
A literal carpet of humanity, as the source implies. It means people theoretically standing on the absolute highest peaks of Everest, perched on the edge of volcanoes, packed densely across the Sahara, the Gobi, Siberia, every desert, every frozen plain.
I want to dig into that definition a bit more. The source specifically says it includes the polar ice cap land mass. Why is that detail important?
Yeah, that's a key methodological point. It treats the Earth like a solid ball with a surface layer. Right now, the big ice sheets, Antarctica, Greenland, they sit on continental rock.
So they count as land for surface area purpose.
Exactly. They're considered land masses, effective. Massive stationary platforms of ice top of land. So by including them, the source is using the maximum possible land surface area measurement we have today.
Okay, so it's a snap. If those ice caps melted?
Then that surface area wouldn't just disappear. Some of it would become ocean.
Right. So the land number, the 148.9 trillion, would actually shrink slightly.
It would. And the sea capacity number, which we'll get to, would grow. It shows how this is really about classifying surface area.
Okay.
And we're also talking about covering every cliff face, every deep ravine, every meter of complex coastline.
Coastlines are tricky, aren't they? That whole fractal thing.
They are. The measured length changes depending on how fine your ruler is.
Mm-hmm.
So the source has to, apply some mathematical smoothing to get a neat number like 148.9 trillion square kilometers of land.
So it's a standardized measure of the total surface.
A highly standardized measure, yes.
Yeah. Okay, so we've got 148.9 trillion covering every peak, dune, ice cap, every possible bit of solid ground. Let's circle back to the implications we have to ignore for this math to work.
Right. The uniformity implications are, they're staggering.
Mm-hmm.
And they really underscore how theoretical.
Because at 1 person per square meter,
there's zero space for anything else.
Mm-hmm.
Imagine trying to walk across this human carpet.
No room to pass. So that means absolutely zero infrastructure. No roads, no buildings.
No houses, schools, hospitals, power lines, nothing.
And, crucially, no space for resources.
None whatsoever. No farms, no solar panels, no wind turbines, no mine, and critically, no space for weight. Where does anything go?
Right.
The calculation is purely about the standing room. It completely eliminates the messy, three-dimensional reality of human existence.
It really highlights that conflict between pure math and, well, reality. The math says, here's 148.9 trillion square meters.
And reality says, yeah, but we need that land to do stuff, not just stand on.
So the takeaway is that this number, 148.9 trillion, represents the absolute unassailable mathematical maximum for the land we currently have. It's the edge of the possibility space for solid ground.
Precisely. Based on current geography and that one strict rule.
But here's the kicker. That huge number, 148.9 trillion, it seems unimaginably vast.
It does.
And yet, we've only covered about 29% of the planet's total surface.
Just the land portion.
Yeah. Even after packing 148.9 trillion people onto every bit of land, we've only dealt with the smaller fraction of the Earth's skin.
The vast majority is still untouched by this calculation.
Which means we have to confront the dominant surface feature of our planet. And here's where it gets really interesting.
We have to talk about the oceans.
Right.
So, to cover the other 71% of the globe, we need to embrace the fantastical assumption that the source calculation requires.
Yeah, this is the big leap, isn't it?
It is. Since most of the surface area is water, and this is purely about surface area capacity, the calculation demands we assume the ability to occupy the marine surface at the same density.
1 person per square meter standing on water.
Essentially, yes. The source is explicit. Assume the ability to stand on the water's surface.
It's not about floating cities or anything technological. It's pure geometry. Imagine that continuous layer just extending over the sea.
Exactly. We're firmly in thought experiment territory now. The Earth's total surface is about 510 million square kilometers. Take away the land.
And you're left with that massive 71% covered by oceans.
And if our deep dive is strictly about measuring total surface area in human unit, mathematically we just cannot ignore 3/4.
It forces the question, if somehow you could stand on water, what would the capacity be? The math has to answer that.
The math demands it, yeah.
Okay, so 148.9 trillion fills the land. How many people does it take to cover the entire sea surface area? Same rule, 1 square meter per person.
Get ready for the next colossal number.
The number needed to blanket all the oceans, seas, everything is
361.1 trillion.
Wow. Okay, just put those side by side. Land, 148.9 trillion.
Sea, 361.1 trillion.
The difference is huge.
It's immediately obvious, numeric. The ocean capacity is roughly 2.4 times larger than the land capacity.
2.4 times that comparison. That's what makes this so powerful, I think. We hear Earth is 70% water all the time.
Right, it's an abstract fact.
But translating it into these people units gives it real weight. The oceans represent 2.5 times more standing room surface than all the continents put together.
It completely flips our usual perspective. We think of the continents as the main stage where everything happens.
Yeah.
But mathematically, purely in terms of surface area, the land is dwarfed. That 361.1 trillion captures the sheer vastness of the Pacific, the Atlantic, the Indian Ocean, all the sea. A continuous human layer covering almost 3/4 of the globe.
A seamless skin over the water.
Let's dig into that scale a bit more.
Okay.
361.1 trillion. We're talking about covering water thousands of miles off, over the abyssal plains, miles deep.
Directly over the Mariana Trench.
Directly over the deepest point, yeah.
Yeah.
The Challenger Deep. Uniform coverage, 1 square meter per person everywhere.
Even the curve of the Earth comes into play at that scale, doesn't it?
It does. That layer of 361.1 trillion people would essentially form a slightly curved skin following the ocean's surface, really emphasizing the two-dimensional nature of this whole calculation.
It also highlights a difference from the land calculation.
Yeah.
The land has all this complex topography, mountains, valleys.
Which adds complexity, but maybe not as much raw area as you'd think compared to the ocean.
Whereas the ocean surface, relatively speaking, is much smoother. Geometrically simpler, perhaps?
Simpler in terms of large-scale bumps, yes. Which simplifies the geometry, but maximizes the sheer continuous area involved in the 361.1 trillion figure.
And that's the geographical lesson here, isn't it? Keep the density constant, 1 person per square meter.
Right.
And the resulting population numbers become a kind of high-fidelity map of surface area.
Exact. The 361.1 trillion prove, with this almost unbelievable scale, just how much more surface the water covers than the land. If we didn't make that stand-on-water assumption,
we'd be ignoring 71% of the planet's geometry in this specific thought experiment.
Precise.
It totally shifts the perspective. We stop being just land creatures on continents.
And start seeing the planet as this sphere with 510 trillion potential square meters of surface, most of which just happens to be wet.
Yeah. It clarifies that all our current civilization, all our challenges with 8 billion people, they're happening on that smaller 148.9 trillion square meter fraction.
While the oceans represent this enormous mathematically defined hypothetical reserve of pure surface area, untapped space in this very specific theoretical sense.
Okay, the moment of synthesis, we take the land capacity, 148.9.
Check.
We add the hypothetical sea capacity, 361.1 trillion.
Check.
Add them together, and we arrive at the absolute theoretical maximum physical density of the Earth's entire surface under this one rule.
The grand total.
The grand total global capacity is exactly 510 trillion people.
510 trillion. And again, that number isn't arbitrary. It's simply the total surface area of the planet, land and sea, measured in square meters.
It's the geometric boundary condition.
That's the perfect term for it.
It's kind of elegant, actually. Despite the fantastical standing on water part, the final number is just the total area.
510 trillion square meters equals 510 trillion potential person spots. It's the absolute ceiling for two-dimensional occupancy based on the premise.
And what's powerful is seeing how the pieces add up, confirming basic geography.
Exactly. Look at the ratios again. Land capacity, 148.9 trillion divided by the total, 510 trillion.
Comes out to about 29.2%.
Right. And the sea capacity, 361.1 trillion divided by the total.
70.8.
Spot on. So the population breakdown itself becomes this high-fidelity numerical map confirming the 70-30 waterland split of the Earth's surface.
The math forces us to see that geographical reality by translating area into this slightly mind-bending quantity of people.
And thinking about that boundary condition is key. 510 trillion is the hard limit. Imagine you reach that point. The entire surface, land and sea, is covered.
Shoulder to shoulder globally.
Then one more person arrives.
Yeah.
Person number 510 trillion and one.
What happens? The calculation breaks, right?
It has to. Because where do they go? There are only two possibilities mathematically, and both violate the original rule.
Okay, what are they?
Option one, the density has to increase. That extra person must occupy space already taken by someone else. They have to physically overlap somehow.
So you've reached maximum horizontal compression. The single layer isn't single anymore.
Exactly. It starts to compress or stack horizontal. Option two is maybe easier to picture, but it's explicitly outside the source's calculation.
Vertical stacking.
Vertical stacking. If you insist on keeping one person per square meter of footprint, that extra person has to stand on top of someone else.
Starting a second layer, taking it into the third dimension.
Right, which the source calculation wasn't about. It was strictly two-dimensional surface area.
So 510 trillion is that precise mathematical line where 2D occupancy failed. Doesn't matter where that extra person tries to fit Arctic, Pacific, peak of Everest, the space defined by the rule is full,
forcing either compression or verticality. It really hammers home that the ultimate constraint in this calculation is simply surface area itself. It doesn't care if it's mountain or ocean. If it's a square meter of surface, it counts towards the 510 trillion.
Yeah, I think for me, the biggest geographical shock is realizing that in this abstract sense, the problem isn't scarce land. It's finite surface area.
Yes.
And the land is just the smaller part of that finite total. The sheer scale of 510 trillion totally reframes the discussion around planetary geometry, even if it's purely theoretical. Okay, let's quickly recap the power of this. That 1 square meter rule constant.
It's the measuring stick.
And the huge numbers that result, they just reveal the geometry of our planet. The numbers themselves are almost too big to forget, right?
They are pretty staggering.
So what does this all mean for us thinking about?
Well, it means the land area, which feels so vast to the 8 billion of us now, is mathematically dwarfed by the rest of the planet's surface. This whole exercise gives us a unique perspective on limits. It clarifies that the ultimate physical limit is surface area.
And we are incredibly far from that purely mathematical seal, hundreds of trillions away.
It defines the absolute edge of the possibility space, geometrically speaking.
And seeing that 361.1 trillion number for the oceans, it just drives home how much of the Earth's skin we simply don't and probably can't ever use for standing room.
That vast, wet majority. Hashtag outro.
Wow. Okay, this has been a truly monumental deep dive into scale. Let's just quickly lock in those 3 core numbers one last time for everything.
Good idea.
We have 148.9 trillion people theoretically needed to fill all the...
Got it.
And they're 361.1 trillion for the hypothetical capacity, assuming you can stand on water.
Right.
Giving a grand total global maximum capacity of 510 trillion, based purely on surface area at 1 square meter.
510 trillion. That's the absolute geometric limit based on the source's rules.
Understanding scale like this is... well, it's crucial for thinking about global anything, isn't it?
Absolutely. These numbers redefine global capacity in a purely mathematical sense. It's a theoretical anchor point.
Which raises, I think, an important final question.
Go on.
We've established 510 trillion is the maximum space capacity, pure geometry.
Yes.
But we all know this scenario is impossible in reality. Why? Because the second you add back even one practical constraint.
We'll think classes.
Right. Say instead of 1 square meter, people need 2 square meters, maybe just a little elbow.
What happens to the total?
It instantly halves. 510 trillion drops to 255 trillion.
Wow. Just 1 extra square meter wipes out half the potential population.
Or more realistically, think about needing a tiny patch of land to grow food, or space for energy, or just space between people.
Any resource need, any logistical requirement makes that 510 trillion number plummet astronomically fast.
Yeah.
It shows how fragile that maximum number is. It's not physical space limiting us today.
It's everything else. Logistics, resources, sustainability.
Exactly.
So here's a final provocative thought for you, the listener, to mull over. We know the Earth can theoretically hold 510 trillion people based purely on surface area.
The geometric maximum.
So you should consider, if you had to pick just one single non-space constraint, forget density, think about a necessary resource or system, which single factor do you think would crash that 510 trillion number down towards our current 8 billion, the fact?
Is it fresh water availability? Is it the energy required? Is it the sheer amount of land needed for a functioning ecosystem, not just standing?
What's the bottleneck that shrinks the theoretical maximum most drastically? That question, I think, takes you beyond the source's pure math and into exploring the real-world constraints on planetary capacity. Something to think about.